Hi, my name's Ben. Today I'm going to be talking about curvilinear motion. So when we have a curvilinear problem, that's a problem where you're moving around a curve. We can approach it using XY coordinate systems, like we would with most projectile motion questions. Or we can use a new coordinate system, the normal tangential coordinate system. Now the normal tangential coordinate system is different because whilst the XY coordinates are fixed in space, the normal and tangential coordinates move with the object you're analyzing. The tangential, tangent to the path, and the normal, perpendicular to the tangential. So that's what I'll be focusing on today, and to help me, I'm going to use an experiment. So in the boot of my car, I have a pendulum suspended off a series of strings. Above that I have a camera that can film the motion of the pendulum. Underneath I've got a grid.
Each black grid line represents a 5-degree change in angle of the pendulum, and each red one a 10-degree change in angle.
So as I drive my car, it experiences a variety of different accelerations. As I start the car, it experiences a tangential acceleration. If I negotiate a corner, then we'll be experiencing a normal acceleration. So before we analyze the data, we first need to derive an expression for the acceleration based on the angle of the pendulum.
So this is our pendulum. It makes an angle of theta to the vertical. It's got two forces acting on it. It's got the force due to gravity, mg. It's also got the tension force. Now we can split the tension force into its vertical and horizontal components, t cos theta and t sin theta. Now we're going to assume that when I'm taking my measurements, there's no movement up or down, so the sum of the forces in the y direction equals 0. Solving that equation, we get t equals mg on cos theta. Now in the x direction, it is accelerating, so sum of the forces in the x equals max. Solving that equation, we get ax equals t sin theta on m. Substituting back in our value for t, which we got above, we get that ax equals g tan theta. So let's try this out, first with an acceleration in the tangential direction. As I take off, you can see that the maximum angle the pendulum makes is around here, which is about 25 degrees. So, back to our formula for acceleration. Acceleration equals g tan theta. We know that g is 9.8, theta is 25 degrees, so evaluating that gets us 4.6 meters per second per second. Now if we make the rather large assumption that acceleration continues, my high-powered sports car can reach 100 km an hour in only 6 seconds.
Now how about we try a corner?
In this case, we have acceleration in the normal direction, because we need that acceleration in order to have motion around a curve. As you can see, it peaks out around 17 degrees. Now back to our formula. When we substitute in g of 9.8, theta of 17 degrees, we get that our acceleration is 3.0 meters per second per second.
If I am in fact moving in a circular arc, then the acceleration I'm experiencing is called my centripetal acceleration.
We actually have a formula for that. A equals v squared on rho.
So using that, we can determine the radius of the corner I just turned.
So, n equals v squared on rho. Rho is what we use for the instantaneous radius of curvature. Now 28 km an hour is 7.8 meters per second. So, substituting that in, we get that rho, the radius of curvature, is 20.3 meters.
So one thing to keep in mind when we're doing curvilinear problems and using nt coordinates is that since the normal tangential coordinates move as the point of interest moves, the velocity is always in the tangential direction. We never have any component of the velocity in the normal direction.
So, when I'm taking a corner, as my car moves around, so too do the normal and the tangential axes, such that the tangential axis is always in the same direction as the velocity. However, we can definitely have acceleration in the normal direction, as you can see when we go around a curve.
So thanks for watching. I hope you learned quite a bit about curvilinear motion, and I'll see you around.